this eigenvalue from? So what is lambda in this case? That's interesting that all three operators have plus or minus 1 as eigenvalues. And what are the states?
Should be the same. It's the same eigenvalue.
So no, it's a different operator. We are looking at this. What are A and B in this case?
Plus minus IA.
So you basically have what states? Right? So to summarize, we have this. SC, which is h bar over 2, 1, 0, 0, 1. We have eigenstates which are up, and I will put z direction here, up in z. Actually, probably the better notation is put like this, up along the z direction, right? So this eigenstate is this. Down by z is 0, 1. For Sx, it's h bar over 2, 0, 1, 1, 0. So then we have up in the x direction is 1 over square root of 2, 1, 1. And down in the x direction is 1 over square root of 2, 1 minus 1. SC, sorry, SY, which is h bar over 2, 0, minus I, 0. So then up in the y direction is 1 over square root of 2, 1 I, and down in the y direction is 1 over square root of 2, 1 minus. These are three different bases that you can use. So you can see something. A state which is in the up direction along the z-axis is probably a linear combination of these two. Because we can always write up, let's say in the z direction, which is 1, 0, which I can write as a linear combination of these two. So I can write it as alpha up in the x direction plus beta down in the x direction. But this is wrong. Say if I want to write up in the z direction, up in the x direction plus beta stay in a y direction. This is wrong. You know why? Because I cannot mix states from the two different bases. I can either use states which are diagonal along the x-axis or along the y-axis. So this cannot be true. This can be true, or this can be true. But you cannot mix x and y here because they belong to different bases. So how do we find these coefficients, alpha and beta? It's actually not very difficult. It's a basic linear algebra, right? So how do I find alpha and how do I find beta? Well, we take this state in the z direction, which is alpha, this state in the x direction plus beta, this state in a y direction. So if I want to find the coefficient,
You can't mix those, can you?
huh?
You can't mix x and y.
Thank you.
No, no.
Just checking, paying attention. No, I didn't. Although it came out as if I did. But thanks for paying attention. So how do I find this alpha? Like you find coefficient of any vector, you just multiply this whole combination by this vector from the left using the scalar product. So what we do is we take this, multiply it by up in the z direction. So this will give us alpha up in the x direction, up in the x direction, plus beta up in the x direction times down in the x direction. These two are orthogonal. You can check. This is 0. This is 1. And now we just need to compute this. And this is easy. This is actually this vector. Complex conjugated, right? Emission conjugated times this matrix, which is 1 over square root of 2, 1, 1, 1, 0, which is 1 over square root of 2. So alpha is 1 over square root of 2. Likewise, you find beta to be 1 over square root of 2.
Alpha and beta still have to add up, their squares still have to add up to 1.
Yeah.
Yeah.
But this is automatic.
Right.
You can see it also another way. So for example, if you look at this state in the x direction, which is 1 over square root of 2, 1, 1, right? So I can write that as 1 over square root of 2, 1, 0, plus 1 over square root of 2, 0, 1. So then you can see immediately that this state is 1 over square root of 2. This is up in the z direction, right? Plus 1 over square root of 2. Down in the z direction. And then if you look at this state, this is 1 over square root of 2, 1 minus 1. So this is 1 over square root of 2. Up in the x direction, minus 1 over square root of 2. Down which actually tells you that you now have a linear combination. And then you can solve for these two in terms of these two. If you add them up, so you add these two states, these will cancel. And so you will get 2 times square root of 2. So this will give you 1 over square root of 2 up in the x direction plus 1 over square root of 2 down in the x direction. If you subtract these two, right, then these two will cancel and these two will add up. So you can get that down in the z direction. It's 1 over square root of 2 up in the x direction minus 1 over square root of 2 down in the x direction. For y's, you do the same thing. And now you can answer all the questions that you care to answer or that you can actually reasonably ask. What is the chance that state which was prepared to be along the z direction has actually a spin pointing along the x direction? It's a coefficient squared, right? Which is 1/2. This is your 50%. Now, the question that we have asked is slightly more complicated. We have asked if we prepare the state to be initially in the up direction along the z-axis, what is the chance that that state has a spin along the x direction at a later time? So how do we answer that? For that, we actually need to solve the Schrödinger equation for the Hamiltonian that we have it, which describes this system. And see what a state initially prepared to be in the z direction along the z-axis evolves into, and then we'll do this multiplication and determine the coefficient at a later time. So let's do that. Partially what I'm trying to convey to you is that there isn't really much to do in quantum mechanics. What makes it complicated is that systems, Hamiltonians, become more complex, so the Schrödinger equations are more complex to deal with or solve. But once you find the solution of the Schrödinger equation, which is not necessarily the easiest task in the world, questions that you ask are just questions like these, and their answers are found exactly the same way as we are defining them here. Results may look more different because simply of complexity of the Hamiltonian itself, but you cannot ask any more complicated questions than what we are asking here. And then these chances, these probabilities that you find, they can be used for calculating other useful things. And what these other useful things depend on a physical context, and so on. Typically what you are interested in chances that two things will scatter off of each other. So you are basically dealing with a scattering problem, and you want to find out, how likely is that a certain scattering process will produce these or those things in a final state. Say you have a scattering of an electron with an atom. You are interested, whether the electron will recoil in what direction, whether perhaps it will be absorbed, or maybe whether light will be emitted at the same time in the process. Or if you are starting with an object which can actually survive for some time and then decays, you may be trying to figure out how long that object lives before it decays and what are the products of the decay. So it's about formulating questions after you have actually chosen a certain discrete way of describing your system, and then calculation relatively simple in principle, although maybe hard in practice, provides you with these answers which can be used with some other things. So which actually describes what we need to do. First we should learn how to solve Schrödinger equations by hook or by crook. It really doesn't matter. Then how to formulate these questions which can be answered within the framework of quantum mechanics, and then possibly how to use these answers to compute interesting quantities which can actually be measured. Because probabilities, unless you craft experiments very carefully, are not directly measurable. I mean, they are measurable indirectly by doing certain experiments and then computing, reading some dials on the instruments and then inferring based upon these readings what has actually gone on. So we have the Schrödinger equation defined by this Hamiltonian. So this is the state I H bar. And this state can at any time be described as some coefficient A of t plus some coefficient b of t. And now you have your choice. You can either use here up along z and down along z, or you can use or x or y. So you have your pick which basis states to use. But you're going to use either z or x or y. You cannot use x here, y there, or any combination. So either it has to be both z or both y or both x. So the first thing is to solve the Schrödinger equation. So we have E0, D0, E0, D0. And let's say I'm going to use z direction. It doesn't really matter. So if I use the z direction, then I'm going to have A of t, B of t, I, H bar, A dot of t, B dot of t. So that's my Schrödinger equation. That's a set of two first order differential equations. So if I H bar A dot is E0 A plus B0 B, and I H bar B dot is E0 B plus B0 A. Okay. So how am I going to solve this? How do I solve this problem?
Well, you do second order, or you could do
Okay, let's try your method, second order differential equation. It's not bad idea. I haven't used that method in a long time, so. So if you want to make the second order equation, what do we do? I take the second derivative, I take one more derivative of this will produce A dot, and this will produce B dot, and then for A dot, I just substitute this with B dot, and substitute that. Let's see what happens. So, I H bar A double dot